So here's the problem that we were doing in class. It's similar to the one in the other videos, or the other two videos that I did the other day. It's just now these initial velocities are also at angles. So it's a little more work to unpack what's going on in terms of using your trigonometry. So we have the same two questions where these two objects with masses and initial velocities are going to collide and stick. So they're two clay objects. They're going to stick together. And we want to know what the final velocity is after the collision and the change of momentum or the impulse for each object. I'm going to do this a slightly different way than the other video, but they are both going to lead you to the same idea or the same answers. So we have our first object here with the 5 kilograms in mass and 10 meters per second at 20 degrees below the horizontal. I've already broken the components, the x and y velocities there, 9.4 meters to the right and 3.42 meters down. So then what I did there is I just calculated the momentum in the x direction and the y direction for this object, right? So that's what this calculation is right here. The momentum of this first object in the x direction before the collision is its mass times velocity, right? So there's a difference between momentum and change of momentum. So right now I'm just calculating the momentum. So before this collision, we have a momentum in the x direction of the first object of 47 Newton seconds, right? 5 times 9.4. Again, this is the x direction, so the mass times the x velocity. I did the same thing for the y here. Super important to note that the y velocity is negative. I didn't define it, but we totally should. Up is positive, to the right is positive. So for the fact that this velocity is pointing downwards in the y direction, it is so important that we remember that this velocity in the y direction is negative. Okay, so the momentum of this first object in the y direction is negative 17.1. I did the same exact thing for the second object. I broke it into its different component velocities, and then I also talked about the initial momentums of this object in the x and y direction. So that's kind of just something I did to start. Now we can start talking about what the final velocity is after the collision. I'm going to take it through with the momentums and show you how we can get to the final velocity after that. So again, anytime we have components, we should keep it in those components. Okay, so let's talk about the x momentum, and we know that the p total x before the collision is going to equal to the p total. Stay away from total. We'll just talk about the x. So we know that px before the collision, px naught, is going to be equal to px final. Because the conservation of momentum says the momentum before the collision and after the collision is going to be conserved. So we have two momentums in the x direction before the collision because we have p1, right, p1 x naught and p2 x naught, and that is going to be equal to the momentum. There's only one object after the collision, p1 plus 2 xf. Okay, so since I have these momentums already written out, I can just plug in. There's 47 plus 35.98. It's going to be equal to, right, the p1 plus 2 xf, and that is going to be 82.98 Newton seconds. Okay, so this, when this collision is done, there is going to be some x momentum for this final object that is 82.98 Newton seconds to the right. Oh, I'm using the wrong, that's my problem. I'm really sorry. Oh yeah, that is the right thing. I'm thinking of something different, sorry guys. The unit for momentum is also Newton seconds or kilograms meters per second. They're the same. Anyway, so we can do the same thing in the y direction, where we can say the momentum y before the collision is going to be equal to the momentum y after the collision. Again, we have two objects that have initial y momentum, and that is going to be equal to the momentum y after the collision. So already calculated PY1 PY1 is a negative 17.1, right? Because remember, it's going downward. And the second momentum is going upward. That's going to be equal to P12YF. And that is equal to 17.1, which is negative, plus 42.91, which is 25.81 Newton seconds. Okay, so if we put these two together, these are the components of the momentum. So I get 82.98, right, is the momentum going to the right after the collision, and then we have a 25.81 Newton seconds going up. So our question is, what is our final momentum? Right, we use Pythagorean theorem. Again, I'm not showing it because we are so used to using it now. Oopsies. 82.98 squared plus 25.81 squared, square root. We get 86.9 for our hypotenuse. So we have a momentum now that's moving at 86.9, and we need to get this angle. We're going to use the tangent opposite over hypotenuse, and we're going to do the inverse of the tangent, and this is 17.3 degrees. Okay, so our final momentum, this is our total momentum here because we put our two components together. So I'm going to say P total final is 86.9 Newton seconds at 17.3 degrees. And what I can do with this now is I know that the momentum, right, after our final collision is the mass times the final velocity, right? Mass 1 plus 2 times the final velocity. And the mass of these two objects is going to be 5 plus 7 times VF, and that's equal to this 86.9 that we got. 86.9 divided by 12. We get a VF equal to 7.24 meters per second. And the thing is, these are, the momentum is a vector, the velocity is a vector. So whatever direction the momentum is pointing in, that's also the momentum of the velocity. And that's true for even our one-dimensional collisions. The momentum itself, right, not the change of momentum, but the momentum at that time is in the same direction as the velocity because the way the calculation works. So this velocity is also going to be at 17.3 degrees. Okay, so that's another way to find our final velocity. You can compare this to the video that we saw on the other page, and you might be saying it looks like, you know, this might be a little bit more work because the other one we got velocities directly and then put those together as our component, as our, you know, components, and did the Pythagorean theorem with that. But this kind of sets us up a little bit easier for our next question, whereas the other one set us up easier for the other question. So it's just a preference of what you want to do. We still use the same guiding principle that the momentum is conserved. I just wanted to show you two ways to get the same answer, and then a second video will be showing how we can get the change